All right, so we all hear about how quantum computers are going to change the world, right? Solve these impossible problems. But to get there, we've got to solve some of their own really tough problems first. And today, we're going to dive deep into one of the biggest roadblocks, and more importantly, how a whole new generation of brilliant minds is just smashing right through it. So what do you think it is? No, it's not the crazy cooling systems or some rare precious metal. It's something way smaller, way more fundamental, and just incredibly expensive to make. Seriously, this one little component is a massive bottleneck, and the race is on to figure out how to use as little of it as humanly possible. Okay, so here's the game plan. First, we'll break down exactly what this quantum cost problem is. Then, we're going to jump into the arena where the world's brightest minds went head-to-head to solve it. We'll meet the winners, check out their amazing strategies, and wrap it all up with the single biggest lesson we can learn from what they did. All right, let's get into it. What is this super expensive ingredient? Well, it all comes down to the basic operations, what we call gates, that actually make a quantum computer run. And here's the thing, not all gates are created equal, not even close. The best way to think about this is like you're making a movie, right? Most of your shots, your everyday scenes, those are your Clifford gates. They're fast, cheap, foundational. They get the job done. But for those huge, spectacular, mind-blowing scenes, the ones that make the movie, you need special effects. And in the quantum world, those special effects are the T-gates. You absolutely need them to unlock the full potential of a quantum computer, but man, do they blow up the budget. So why? Why are they so expensive? Well, it's because making a good, reliable T-gate isn't simple. It takes this really complex, messy, and error-prone process called magic state distillation. It's just a massive drain on the computer's resources, and honestly, a huge source of potential errors. So the takeaway here is simple, but absolutely critical. If you want to build a real, working, fault-tolerant quantum computer, you have got to be incredibly stingy with your T-gates. So, this huge T-gate problem, it's so important that it actually became the main event, the centerpiece of a huge international competition designed to find a solution, and fast. And that brings us to iQuHACK 2026, the MIT Quantum Hackathon. Get this, over one single weekend, you had more than 1,400 people from 76 different countries all coming together, either in person or online, for one reason: to take on the Superquantum challenge. And you guessed it, the whole thing was about T-gate optimization. The mission, if you chose to accept it, was crystal clear. Every team got a bunch of quantum circuits, and their job was to rewrite them using only those cheap Clifford gates and as few of those expensive T-gates as possible. The winners, they'd be the ones who could do it with the absolute minimum number of T-gates, all while making sure the final answer was still accurate. Every single T-gate saved was a victory. So, after this massive, intense, global showdown, 4 teams rose to the top. And what's so cool is that each one came at the T-gate problem with a completely unique and powerful strategy. And here they are, our code breakers. From the on-site and remote tracks, let's meet them. Lil Luna, the Q Factor, QON, and random_kangaroos. I love that name. Like I said, each team had their own playbook, so let's dive in and see exactly how they pulled off these wins. All right, first up, let's talk about the on-site winners, Team Lil Luna. Their secret weapon, their whole philosophy, you could boil it all down to just 2 words: structure matters. And this is so important. They didn't just use some generic one-size-fits-all compiler, no way. Instead, they looked at every single one of the 12 challenge circuits as its own unique puzzle. They were hunting for the hidden mathematical patterns inside. And that custom-tailored approach, it's just way more efficient because you find the specific shortcuts that each individual problem gives you. They had this incredible intuition. They could see which problems could be solved using only the cheap Clifford gates, which is a huge win. And for the tougher ones, they used really clever approximations and other tricks to just slash that T-gate count. It was just a masterclass in how to balance precision with that super high resource cost. Okay, moving on to Team the Q Factor, who nabbed 3rd place in the on-site competition. Their angle was all about practical, down-to-earth, real-world efficiency. You could really tell they were thinking like engineers try to build an actual machine. They treated every single T-gate like it was gold. They were just relentlessly hunting for ways to get rid of them, one by one, with these really aggressive hands-on optimizations. I mean, their whole approach was a perfect mirror of the mindset you need to build actual fault-tolerant quantum hardware. All right, now let's hop over to the remote track. And this is where things get really interesting, because Team Random_Kangaroos came in with this totally fascinating perspective from what seems like a completely different field. And this is just a brilliant example of how powerful it is to think outside the box. They realized that these techniques, called Reed-Muller codes, that are normally used for something else entirely, quantum error correction, protecting the quantum info from noise, could actually be repurposed to optimize circuits and slash T-gates. And in this crazy, intense 24-hour sprint, they managed to solve all 12 circuits and prove just how powerful that connection is. Wow. And last, but certainly not least, we've got the first place winners from the remote track, Team iQuHACK. And folks, they delivered what might just be the most systematic, most powerful solution we saw in the whole competition. Their whole philosophy was exact when possible. They didn't mess around with approximations if they didn't have to. They used this powerful set of mathematical tools, this algebraic toolkit, to find these perfect, elegant solutions that needed almost no T-gates. And for the really tricky problems, they started combining advanced techniques to squeeze out another 10 to 20% improvement. But the real showstopper was what they did on the bonus challenge. Okay, look at this number, 255. Now, why is that so incredible? Because for the big 9-qubit bonus problem, the theorists had already done the math. They had figured out that 255 was the theoretical minimum, the absolute rock-bottom perfect score you could ever hope to get. And Team Kuhn? They hit it. They didn't just find a good solution, they found the perfect one. That's just mind-blowing. So, when you step back and look at all 4 of these amazing strategies together, there's one really powerful theme that just shines through. And here's the ultimate takeaway. The key to solving this massive T-gate problem, it's not about having the biggest supercomputer or just brute forcing every single possibility. It's about insight. It's about being clever. You had La Luna, who adapted to each problem. The Q Factor, who were super practical. The Random_Kangas brought in fresh ideas from a different field. And QON, who found perfection using deep mathematical structure. Every single one of them won by being smart, not just powerful. What this whole challenge really showed us is that there's this incredible global community of young engineers and scientists who aren't just dreaming about quantum computers. They're actively figuring out how to build them. It proves that real progress happens when you combine that deep, heavy theory with scrappy, hands-on experimentation. And it just leaves you with this one really exciting question, doesn't it? If this is what they can figure out in a single weekend, what problems are they going to solve next?